Hello, we are a group of quantum chemistry for material scientists in KAIST course. We are aimed to introduce some methods of making qubit easily to people who are not familiar to this theme. Then what is qubit? Qubits are just quantum two-level systems such as the spin of an electron or the polarization of a photon and can be prepared in a coherent superposition state 0 and 1 in isolated system. But using qubit, we can store more information compared to bit. There are several ways to make qubits, such as superconductor, nitrogen vacancy center, and 2D materials.
First, I'm going to explain about method of using superconductor. Before understanding method of using superconductor, we have to know the concept of Josephson effect. Josephson effect is almost similar to tunneling effect. Its definition is the phenomenon of flow of currents through superconductor, so there is an insulator between them. Current cannot flow into insulator. Therefore, it can be explained by tunneling effect. Also, we call this connection Josephson junction, and current which crosses this insulator barrier is Josephson current. This Josephson current is actually flow of the Cooper pair which have opposite direction of spin and speed. Although pair of electrons have strong repulsive force as minus charge, phonon can tie these electrons. As you see this picture, left picture represents Josephson junction and right explains the Cooper flow through the insulator. Then, how can we utilize this theory to apply in real life? First of all, by using characteristic of Josephson effect, it can change DC to AC or AC to DC. Therefore, we can make high sensitivity detector of electromagnetic waves. Above graphs represent Josephson device. When microwave passes through the Josephson junction, AC converts to DC. Also, another characteristic of superconductor is that resistance is zero when temperatures go to zero. When we insert the Josephson junction, we can control the current. As Josephson junction's critical current is weak, it can allow small amount of current. Then if we make loop with superconductor, we can make magnetic field sensor or current sensor. Now we can make qubit by using superconductor. Then what is the advantage of using superconductor? As characteristic of resistance is zero in specific temperatures, we can send energy information safely. If not, energy information will be destroyed. When we make the qubit, we use concept of LC circuit. Above graph describes LC circuit and below graph describes Josephson junction instead of inductor. In this case, instead of inductor, we use Josephson junction. The most important point is that we should make energy non-linearity. Josephson junction can meet this condition, however inductor cannot meet this condition. Then we can make capacitor Josephson junction like in this picture. Consequently, we use niobium for capacitor, aluminum Josephson junction as inductor. This can make atom has overlapped energy level of two lower energy states. If we send microwave to resonator, it resonates with energy state. Then we can analyze the signal and get energy level and state of qubit. Finally, we can connect qubits using resonator and make entanglement. However, it is hard to connect, so we cannot connect all the qubits.
Next, let me explain about nitrogen vacancy center in diamond. Here is diamond structure. This structure can be changed this another structure. One carbon atom is changed with a nitrogen atom. Nitrogen can combine with three atoms, so one carbon atom must be eliminated. This color center is called as nitrogen vacancy center, which is consisted of a substitutional nitrogen atom and carbon vacancy. Nitrogen vacancy center can be used in quantum bits by using its nuclear spins and electron spins which are trapped in the carbon vacancy. Also, it has magnetic and electric properties, so it can be used as a sensor of magnetic and electric field. Nitrogen vacancy center has enable properties for a qubit. First, nitrogen vacancy center qubit has long coherence time and it works even in room temperature. Evenly, the time required to manipulate the state of qubit is brief and the measured decoherence rate at room temperature is 1.35 milliseconds. Thus, this qubit can perform 10,000 operations before the state lost by decoherence. Second, it has optical properties because the electron spins interact with photons. Nitrogen vacancy center is so bright, so it can be detected individually with conventional microscopy. Its optical property provide information of its quantum states, and we can read out it. Additionally, the electron spin is not only qubit we have in the system. The electron spin couples to nuclear spins in the environment, which gives us extra qubits to store and process quantum information. It gives advantages as a quantum storage. To make the nitrogen vacancy center qubit, we needed to fabricate the diamond, but it is difficult because of hardness and chemical inertness of diamond. Then how can we make nitrogen vacancy center? We use the chemical vapor deposition technique. I will explain about it. First, irradiate high energy particles to the diamond and produce the lattice vacancy. Then anneal it with a small fraction of nitrogen atoms. Then single substitutional nitrogen traps vacancy and it is aligned to the growth direction. By these processes, we can make nitrogen vacancies in diamond to use as a qubit.
Let me explain about 2D materials now. Based on solid state, single photon emitters (SPEs) are emerging methods of quantum technologies, and with resonators and waveguides, they can be building blocks of quantum circuits. The most investigated method is quantum dot methods, which work primarily at cryogenic temperatures, in other words, low temperatures. The most famous method was nitrogen vacancy center in diamond method, but they remained inadequate despite years of research. However, in 2015, SPE field expanded abruptly after being suggested 2D material method. In 2016, hexagonal boron nitride was the powerful candidate for this one. Hexagonal boron nitride has the advantage of being fairly thin and therefore offers new possibilities for device engineering. It has band gap similar to diamond, around 6 electron volts, and can have wide range of defects that can act as ultra-bright and photostable SPEs at room temperature. Additionally, this 2D material has abruptly made researchers' interest grow. Rapid research is being made to identify this material's characteristics as an SPE, such as super-resolution imaging of emitters of HBN by scanning tunneling microscopy, or modeling the crystallographic structure of potential defects which are responsible for quantum light emission, etc. However, exploitation of 2D HBN is also a topic in material sciences and will require vast advances in fabrication methods. Fabricating defects in 2D HBN can be achieved by using low-energy ion implantation or bottom-up synthesis method. Another way for making quantum computers which compose more than 2 qubits comes from silicon. Silicon-based qubits generally show high fidelity, but interqubit coupling has not yet been perfectly achieved compared to other materials. One way on research to achieve this is positioning qubits really close in order to entangle them, about 12 to 13 nanometers. The way to move qubits in this high precision is to use scanning tunneling microscope. Through this device, we can draw a pattern on silicon with hydrogen atoms in order to guide the qubits in atomic precision. Silicon has 4 valence electrons, and all of the electrons take part in forming lattice structure. Thus, qubit logic gates can be stabilized because there is nothing in the silicon crystal. Additionally, because silicon is a very widely used material due to semiconductors, researchers can use the massive experience of producing silicon that industry developed. Thank you for listening and watching.